My name is Dave Vance, and this video is the advanced topics in the series of videos about SAPP, still another phylogenetic program, which is a program that produces automated trees from YSTRs, YSNPs, and genealogies. In the first video, we covered the main purpose of SAPP, and we covered the three major sections of the input file. That's the /str data, /snp data, and /gen data sections of the input file, and how to combine those in order to give data into SAPP to produce trees that reflect the ancestry of a group of men connected by Y-DNA. This video covers more advanced topics. It covers some of the other input sections, why you would want to use them, how you use them to add to your tree, produce different effects in your tree, and change how SAPP calculates its most likely branching and modify that. We'll get into some very cosmetic changes, things that simply change colors and information on the picture. We'll also get into more advanced topics that are mathematical based, TMRCAs, STR mutation rates, and how those are used and how to vary them within the tool. So we will span the gamut between very technical, very statistical, and very cosmetic changes of the tool, and we'll do it in this order. So I'll first touch on some cosmetic options, /info, /colors, and /groups. To a certain extent, we'll cover how TMRCAs and the way they're calculated in the tool, how SAPP used them for estimating. That's not necessarily a deep dive into those statistical calculations, but you'll get a sense for how they're done and where to go for more information. I'll talk about the Snip Tree and the internal tree that SAPP uses in order to make SNP decisions and how to affect it. We'll cover other options here in numbers 4, 5, and 6 that start with some very simple changes and the effects that has, and then talk about more complicated, a little more technical details about how to modify SAPP's programming, and then a few other option parameters that you may want to use as you go along. So hopefully this will give you a good overview of the possibilities of SAPP, how to change some of the parameters to perhaps get a different output of your tree. And if some of this aren't things that you need to cover at the moment, that's fine. You can simply know about them and use them if and when they ever come up. The first topic that we'll talk about are the cosmetic options. Now, these have no effect on how SAPP produces a tree. They have no effect on the internal calculations at all. They're simply used to change the output tree in various ways. So let's start with, on the left in the green box, we have some sample some sample input. It's been a little simplified. Obviously, I have 4 kits here that have long strings of STR values. I've not reflected them all on this chart. For SNP data, we've put down that there are 4 SNPs that we know of that are important to this group. There are the positive and the negative values for those in the SNP data section. And then for gen data, I have John Smith, who only has 2 descendants that we know of. If you remember the first video, this is one of the examples that I've used in the first video, so hopefully this will be familiar. And SAPP has taken this input and drawn a picture with 4 kits underneath, 2 nodes in blue, John Smith being the ancestor of kits 2 and 3, and then it shows the STR mutation history for there, and it puts a few of the other SNPs on the tree as well. Now, let's suppose that I add to my input file, and I give it 3 sections. So a first section is /info. What this does is it adds text to each box. You can also put nodes in here, but it adds information to each box, any information that I want really. If you put too long of a string of text, it will split it over several lines. It's not necessarily the best formatted in the world, but it's intended really just to put short information pieces in each box to allow you to recognize beyond the kit number who that individual is. Now, be very careful with this. This can be private data. It can make the output tree reflect data that is subject to privacy controls. So depending on what country you live in, I would urge you to obviously study up on the various privacy concerns in those various countries and the legal ramifications and regulatory issues, so that you're aware if you distribute the tree or if you put it up on a website, whether or not you've added data that could be taken to be private data in any particular jurisdiction. That said, you can add to the tree /groups also allows you to add, if you notice, there are two kits here that I've put 3 and 4. I've simply put a note, and in this case I chose to put a note that said big Y pending. So in that case I can find on the tree quickly individuals that belong to a particular group that I want to keep track of for some reason. In a very similar way, I can use the /colors section. There are 10 predefined colors, so I can go from 1 to 10 in this first parameter. Then in parentheses, I put all the kits that I want to be of that color. Now, I don't have control over the first kits of from 1 to 10. I simply choose them by number. So in this case, I've decided that kits 2 and 3 should be of color 1, which is this very bright purple or magenta here. But I can also put, instead of the numbers 1 to 10, I can put what's called the RGB values, the red, green, blue values, for any color that can be represented on a computer monitor. And that will translate any given kit or node. In this case, I've chosen to assign node 5, which has this number here, to that RGB set, which happens to be this sort of pinkish orange here, and that changed the node for John Smith. Now, why I would want to do this particular example, I don't know. This simply shows you a different example of how these 3 sections can work. So, to recap, /info gives you the information within the boxes. /groups gives you the information above the boxes in red text. And /colors gives you both the single colors. If you want to choose the group numbers from 1 to 10, you get a predefined color scheme, or you can put your own colors in and decide for any node or kit for that matter, and decide what colors you want them to be. So this gives you a lot of creative control over the output that SAPP gives you. Mostly this would be useful. I use /info typically to put the last names on the tree so that I can quickly see. SAPP doesn't use last names in figuring out its tree, although you can put them into a gen data section in order to force them to be together. But I just use the /info in order to add the last names onto the tree for reference purposes. Also, similarly, groups may be used either for known descendants of a person to see how they appear on the tree if you haven't added that genealogy to the tree yet, or to follow certain kits that may be problematic. Perhaps you have a known set of people that you think are subject to convergence. You want to follow them as SAPP produces different trees based on different options. You can quickly put them in this way and follow them around the tree just by noting what the color of the boxes are. So there's various reasons to do this, but like I said, these 3 sections by themselves have absolutely no impact on how SAPP draws the tree. They simply add color and text to various ways, in various ways, on the tree itself. Now, you notice that when I added this last line here, I added an RGB color and I used the node number for the John Smith node right here in order to set that color. I don't know the node numbers until I produce the tree the first time. So obviously, if you're going to reference nodes by number, that is something you're going to do after SAPP draws the first tree. I will add a major warning at this point. It deserves its own slide. That all of the input that operates on nodes, you can use /info for nodes, you can use it in lots of different sections. The inputs help screen on the SAPP tool shows you or tells you exactly which ones you can use the node format with. But a warning is that all of the input that operates on nodes has to be double checked if you change assumptions or if SAPP ever redraws the tree, because it will automatically number the nodes. And if you refer to them by number, if it's changed the drawing of the tree, the number may refer to a completely different node than what you intend after SAPP changes how the tree is drawn. So the optional parameters that use the nodes parameter are /info, /groups, /colors, /calibrate, and /STR Set. If you use any of those with the node designation in your input file, please remember to double check those numbers every time you either add or remove kits to the tree or change options that change the branching, because that will renumber them, and you may find that you're changing the color of a node or setting its date or doing lots of things to it that have no bearing on that section of the tree. It will produce output that you probably don't expect. So that's my major warning for this video about nodes. Let's move on to TMRCAs and how they're calculated. Now, TMRCA stands for Time to Most Recent Common Ancestor. It's a common acronym within the genealogy community to talk about the estimated time that a group of kits will branch back into their common ancestor. Obviously, any two kits will have a common ancestor. The TMRCA of any group of kits is their common ancestor, the one person that they all report back to when you move back up the phylogenetic tree. In this case, the TMR, and there are various calculation methods, several. Bruce Walsh, I think, probably has the first published estimation method, but there have been several adaptations since then. Most of them apply statistical theory to the various STR mutations that have occurred. And more recently, we're getting some SNP-based TMRCA estimating techniques. Those have their own uncertainties. Both STRs and SNP-based estimating techniques have varying degrees of success. It depends a little bit on the group being analyzed, depends how far back in time their common ancestor is. It depends on a lot of factors. For SAPP, at least, the Ken Nordved interclade aging method has worked fairly well. It's an estimated method that uses least squared regression approach to finding the best fit. What that basically means is it's like plotting the best fit line on a graph that has a number of points on it. You look for where the best line occurs that will explain all those points. In this case, the points are the mutations that have happened underneath that point in the tree, and it's essentially looking for a best fit for the age at which all of those could most easily be explained. Obviously, in some cases, the different branches under a common ancestor will have wildly different STR mutations that can drive a larger error range for the estimate. So you'll see in the example on the left, you have an example age in generations and then a translation to an actual date. And then in parentheses, you'll have an estimated error range. The size of that error range depends on the variation in STR mutations underneath that, and where the different points, how far off they vary from the estimated age. So that's the explanation of what the text means. In this case, you can, through the /calibrate option, which I'll talk about later, you can calibrate these to known ancestors. So if you know that all of these groups, that all of the kits underneath a particular node do descend from a common ancestor of a certain age, then you can put that date into the tool and it will reflow some of the dates around it. We'll talk about all of that more in a minute. But the constant warning about TMRCAs, whether they're STR or SNP based, is that they're always very general estimates. So they will be more accurate the more STR mutations have conformed to statistical norms, which means most of the people who do conform will see them being fairly accurate, but either in different sections of your tree or perhaps along the entire tree, if the STR mutations that have occurred among your group are not very are in fact very diverse and very different from the statistical norms for those STRs, then you'll see that they will not necessarily be as accurate, and the true dates may in fact be outside of the error range. So be aware that they should only be used as a rough guide. I tend to use them for are we still talking about approximately the time when surnames are likely to have been in common use? So back about 1,000 to say 1,200 years, depending on the country we're talking about. It could be a little more or a little less. And I compare them across nodes. So as I move up and down the tree, I look for large gaps or small gaps in the TMRCA estimations so that I can see whether a lot of time has occurred between those common ancestors or little. So that gives me an idea of how closely related the kits under those nodes are to each other. So use them, but use them sparingly and use them with the knowledge that they're not necessarily as accurate as we all would love them to be. Now, the actual math that's involved here looks like this. I essentially put this in so that if you'd like to pause here in the video and study it a little bit more, you can see how this works. Now, as you'll often find in this particular video, we're going to switch gears entirely and go talk about the Snip Tree and how the internal Snip Tree is used. Now, this is a rather busy chart, but you'll notice on the left there's a tree of SNPs. It starts down at the bottom with S7834 and grows up to present day with all the various SNPs that have happened since then. This is a fairly common representation of SAPP's internal tree. In fact, if you use the Snip Tree tool that's available on SAPP's main website, there's a companion tool called Snip Tree that will produce these output trees for any SNP that is in SAPP's internal YSNP database. It has approximately 4,300 SNPs at the moment. It's constantly growing as I add SNPs for various groups and various haplogroups. And I'll explain here why I'm adding those to the internal tree and what its purpose is. So if you have the input file on the right-hand side here, this little box in green that talks about the SNP data section, and you have 4 kits again, and you've said L577 is positive for SNP1, SNP2 is positive for these 2 Z SNPs, SNP3 is positive for BY4027, and SNP4 is positive for S7828. Now, if that's all you know, and this is the only input that you're based on, think about it as if someone came to you and gave you those SNP results for someone and you had no access to a tree. You wouldn't necessarily know from that simple explanation of their SNP results what they were positive and negative for and how they would relate to each other. But if you know that you have an internal tree, like this one over here on the left, and you know that L577, Z21269, Z21262, S7827, and BY4027 all sit in this configuration on the tree, you can start to make some assumptions, or not some assumptions, but you can start to draw conclusions, rather, as to how this group is related to each other. For instance, if you have kits which are positive for a SNP on one branch, like L577, they must by definition be negative for a SNP on another branch, like BY4027. So, for instance, kit 1 and kit 3 had to have diverged back here at a given point in time somewhere after Z21262, since they're on different branches of the SNP tree. In the same way, kits which are positive for a SNP on one branch, like L577, have to be positive for earlier SNPs in that tree as well. So when I said that kit 1 was positive for L577, we know then by definition that he is also positive for Z1269, Z1262, and S7828 all at the same time. So if we have the tree, we start to know a whole lot more about how these kits are related to each other than we did if we just see their input in this format. For instance, when I put this input into SAPP, because it knows this tree, it produces this as the output table that says how kits 1, 2, 3, and 4 are related to each other. And if you notice, there are certainly still question marks. For instance, kit 2 we know is positive for these 2 SNPs, but that doesn't mean that we necessarily know his L577 status, because he may not have been tested for that SNP. We don't know for sure. So that's still marked as a question mark down here. But we do know for 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 different relationships. We know just by the 5 relationships that were entered and the fact that we know the internal SNP tree. So what the internal SNP tree really does is it greatly simplifies the need for specifying SNPs. Obviously, you still can specify SNP relationships, and if the SNPs are not in the internal tree, you have to specify more than you would normally. But if they are in the internal tree, it helps greatly in order to sort through the relationships. You can, by the way, add to this internal tree yourself, only for your individual run, not permanently. But if you want to add a branch to the internal tree, let's say you've discovered a lot of additional SNPs through Big Y testing, or for some reason you have a branch that's not in SAPP's internal tree, you always start with a known SNP, like in this case BY11187. By the way, I could have started somewhere further down on the tree. It doesn't have to be a leaf node of the existing tree, but in this case I did for simplicity. And I say I'm going to define a new branch that comes off of this SNP that in this case goes up. It splits once here, splits again here. The format for this is you add the SNPs each on their own line, where the first SNP is a known SNP on the tree and the rest define one branch below that. You can actually take the branch as long as you want. You could repeat lines to make it simpler, or you can put them all in the same line. I took kind of modified approach here and just put each branch on its own line. That makes it a little bit simpler, but there's several ways of specifying this. But essentially, you start with a known SNP, like in this case BY1187, and I say ZP0152 is a descendant, ZP0153 is a descendant from there further. So I've taken this branch over here to the right and defined it. And there's nothing else beyond ZP0153, so I've stopped there on this line. I then start with another known SNP on the tree. Now I added ZP0152 in the previous line, so now it's a known SNP on the tree. I say ZP0152 has another branch that goes ZP0154, ZP0155, and A199. I can then start with ZP0155 because I've already defined it, and say it has another branch that goes down to A120. That's actually just a misnomer here. Those should be the same SNP. You can either call it A120 or A210. But the idea being that by those three lines, you've now added a branching structure underneath BY11187. Now you notice I haven't put TMRCAs. There's no way to enter TMRCAs into this. And SAPP actually uses the STRs for the estimation of TMRCAs. It does not use SNPs for that, at least not in the current version of SAPP. So there's no need to enter the actual TMRCAs here. When SAPP does report TMRCAs on the tree, like all the way down here, it reports that Z7834 has a TMRCA of 750 AD. Those are simply taken from YFUL's database, and they're there for simple reference. They're actually not used in SAPP. They're simply produced in the tree output in order to show you the ones that have estimated dates. And if you do put this section into your input file, SAPP will then use those SNPs, just like any other SNPs in its internal database. It will do all of the sorting that we talked about on the previous slide and use those in order to make the branching closer to the SNP structure. Now, the last thing I'll talk about in the SNP section here is an advanced option that you can use in order to change this internal SNP tree look even more. If, let's say, you decide that the internal SNP tree that SAPP already has is nowhere near what you believe to be true, it's either way out of date or you don't believe where it was taken from, etc., and you want to redefine all of the SNPs under that section and how they branch together, you can simply turn off the internal tree entirely. There's a /options section which has several advanced options in it. I'll talk about all of these at various times in this video. But if you put a /options section in with no db tree as one of the parameters, it will simply forget about the internal tree. It will only use a /snip tree section that you have put in. Obviously, if you don't include one, it will not know anything about how the SNPs relate to each other. But if you do have a /snip tree section, this allows you to not only add a new branch like I've put here, which in this case would become the only branch internal to SAPP, but it really allows you to respecify all of the existing SNPs that are in this section of the YSNP tree and define them yourself. So it's mostly used for changing or for overriding, rather, the internal SNP tree when you want to. Now, I should note this has no effect on the actual internal tree that SNP uses. That still applies to everyone else that uses the tool. This only takes effect for your runs, and it's simply an on-off switch for the internal tree. Now we'll switch gears again and talk about a completely different option. So this is called the text out option. And if you look on this slide, you've got a very large tree here at the top. It's not really intended to be visible. If you look, here are the kits and the nodes, but even if you zoomed in on this, the picture would be way too large in order to effectively analyze. This is a descendant branch of L226. Credit goes to Robert Casey for producing this image. It is 547 kits, and if it were printed, the resulting image would be 104 feet wide by 4 feet tall. Clearly way too large to do any effective analysis. So in these types of cases, or if you just prefer a textual output to a graphics output for your tree, you can, in the options section, again put the word text out, which is a parameter that converts the the graphical tree into this kind of text output. You've got the indented branches with the branch depth marked by this number, and then you've got the kit or the node name, followed by all the same information that you have. It even has the STR mutation history in the italics here. So all the same information is there. This is really either when the tree image gets too large to effectively analyze, or if you simply prefer the text output, you can do either. Now I'm going to switch gears and talk about some very detailed options that you can use if you want to, what I call tweak the tree. If you want to change the output that SAPP has produced because you've decided that your group for some reason doesn't conform to the statistical averages that SAPP is using to make its original branching decisions, and you want it to look differently. Now, these are all very dangerous options. I'll start by saying that because if you tell SAPP to ignore certain things and focus more on others, you are by definition telling it that you want it to produce a tree that conforms to your expectations. And your expectations may be perfectly valid, and that may be the right thing to do, but you also may produce a tree that says exactly what you want it to say, and that may or may not be correct. So I will issue a warning from the start to say be careful with these, use them sparingly, but they can be very useful if you know that you need to change the tree and you want to see how that works. The first one that I'll talk about is called ignore. This one, as the name implies, removes certain STRs from the analysis entirely. So on the left here, you've got a sub-branch of the tree that has taken CDY A and B into account for the mutation history. That's normal. If I put a /ignore line in with the two CDYs, it simply removes them entirely from the mutation history. Now, it would also, if it's made branching decisions based on these, it may also change the branching decisions. It will simply completely ignore what's happened to CDY A and B. It won't even report them, and the branching will be based on other STRs entirely. Now, why would you want to do this? As you may know, STRs are prone to something called convergence over longer periods of time, especially above about, say, 1,500 to 2,000 years or older. Especially the faster STRs can start to become very noisy and mutate frequently along different parallel branches, and it becomes very hard to decide what is a parallel mutation versus a common mutation that a subgroup shares because it descends from a common ancestor. So when this happens, SAPP will take the statistically most likely path in determining its branches, but that's not necessarily the correct one. And if you know that it's different for some reason, or even if you just want to see how the tree will be produced if you do ignore them, you can do this and find out. The format again is simply all of the STRs that you want to ignore on the same line. Here's one with CDY 464, 710, and 712, which are some of the faster mutating STRs. Now, the only other caveat that I will mention, if you look very closely here, you'll notice that the TMRCA has actually gotten younger when you ignore STRs, and that's normal as well, because the math involved essentially assumes that there have been fewer mutations than actual. Even though these are the faster mutating STRs, they will be left out of the age analysis as well, and so the TMRCAs will be produced as slightly younger. So be aware of that if you do use the /ignore parameter. This next option calibrates the TMRCAs that SAPP reports on its chart. So you've got a normal node here with a node number, the STR mutation history, and here in green you've got the time to most recent common ancestor, the TMRCA, is reflected here. In this case, it's decided that this node, based on the STRs below it, has a TMRCA of 1250 AD. And if you notice, the one before it is 1150 AD, and the one after it is all the way down at 1950 AD for whatever reason. In this case, let's say that I know that this node number 96 actually belongs to a known ancestor. The whole subgroup below it I know is related to each other back to this one ancestor, and I know that that ancestor lived in 910 AD. It's a little early to know for sure, but let's say that I do know that, and I've decided to calibrate this TMRCA, or change SAPP's estimate of the age here from, in this case I have a /calibrate section, I say node number 96, and I change it to 910. That's a year designation. So in this case, it has changed node number 96 to 910 AD. It makes the error range exact, so it's 910 AD to 910 AD, since I've told it that exactly. And it even adjusts the generations back for that common ancestor to 37 based on a 28-year per generation estimate on average. So I would do that again if I know that that node represents a particular ancestor that was born there, or I know that for some reason SAPP's original statistically based estimate is wrong for whatever reason. I can adjust it later, I can adjust it earlier. What SAPP does is it will also adjust the later nodes if it has to, and the earlier nodes. Obviously in this case, if I set it to 910 AD and I had a previous node of 1150 AD, that wouldn't make sense. So it actually flows this one back to 900 AD based on this known ancestor point here, and any ones above that it would change as well. So it tries to adjust the tree to make it make sense. Is this correct? I don't know. Again, you're telling the tree to adjust to your expectations as opposed to letting it calculate the statistically based most likely numbers. Whether that's right or not is something that you need to decide, but if you know it's wrong and you want to adjust this before, let's say, you distribute it to a group of people that may all want to catch that error for you, you might want to do this calibration. It's really intended to be a spot change at certain places in the tree where you know that the date is wrong for some reason. If you do this through a lot of nodes, you may find that it will produce some inconsistent results, since it tries its hardest to adapt to what you've told it. But if what you told it is inconsistent in the first place, that may cause trouble. So I'd say, again, use it sparingly, but it can be useful. Now, Calibrate, of course, is a fairly simple option to use. We're going to go on to a few more complicated options here. The first one being /modal. This takes a little explanation if you're not familiar with modal haplotypes. So the mode of a set of numbers, of course, is the most common value represented in that group. So for any STR, the modal is the most common number that's found in the group. And in this case, the modal haplotype is a fairly useful concept in genetic genealogy. It represents the most common, it's the set of most common values for each of the STRs among that group. So for any number of STRs you have, it doesn't matter if there's 37, 67, 111, or however many, you can calculate the most common number that represents, that is found most frequently among the group. So in this case, obviously, here 13 is the most common value, here 24 is, and so on. When you get to ones that have off modals, again, you have a representative number, 14 in this case, 18 in this one, that still represents the most common values found among the group. So that's what SAPP calculates as what's called the modal haplotype for the entire group. And the modal haplotype is important because it usually, if the group is big enough and if it's balanced enough, meaning that they're not all representative off of one branch of the tree below the group MRCA, it usually represents the ancestral haplotype, which is the haplotype that was actually carried by the person who was the group most common recent ancestor for that group. Now, in certain cases, if you have a very small group, or if you have a group where a couple of kits are off one branch and all the rest of them, 30, 40, 50, whatever kits, are off of another branch, and it's not balanced, you may know already that the calculated modal, the most common set of values, is not the ancestral value. Usually that's true for, it's still the ancestral values for a lot of the STRs, but for one or two of them, you know that it's not for some reason. And once you get more into studying modal haplotypes and so on, you get a feel for which ones these are. It's not hard to look at a set of values and pick out the modal, but it's also not hard, if you know the group structure, the SNPs especially, to start looking at the modal haplotype and decide which ones are actually do represent the ancestral haplotype and which ones don't. So in some cases, you may know that what SAPP will calculate as the most common set of values is not representative of the ancestral haplotype of the group, and you want to adjust that modal haplotype. And that's what the /modal section is for. In this case, what I've done is taken a representative group of 4 kits, and I don't know why I know this, but I know that there are several STRs here at the start that are that need to be changed from the modal. So in this case, the third one on the list, the modal is 14. All of them are 14, but for some reason I say that the modal haplotype should be 15 in this case. Again, later we have a 12 where it's normally 14, and we have two 11s where they would normally be 12. So I've decided to change this modal haplotype pretty significantly. When I do this, I have to put in all the STRs, again, under the /modal section that represent the modal haplotype that I want to use. Now, if I only want to adjust a couple of STRs, what I usually find is easiest, the trick, is to produce the output table on a first run, and then simply copy all of these from the modal haplotype that's represented in the table of output that SAPP produces, and then I can paste them back into the input text file and then go over and change whichever ones I want. Sometimes I have to count over to the right STR, but that's, for me at least, that's the easiest way to input the modal haplotype and then adjust the calculated modal to the one that I want. But in any case, here what I've done is I've changed 4 of them. They're here marked in red for emphasis only, that obviously you don't have colors in the input text file. And the output then will use that exact set of STR values as the modal. And as you can see in the output text file, it now says all of these are now off modal, which means that they represent mutations apparently away from the modal haplotype. And so it will then use these for branching purposes. Why is this important? Because SAPP makes branching decisions trying to lead back to the group MRCA having the ancestral haplotype that is defined by this modal haplotype. And in that case, if it decides that the starting point was different, the branching decisions may in fact be different. So this, again, is something that you want to use sparingly. It is a good tool, especially if you have a subgroup that you know is descendant from a larger group, and you know what the values of the larger group were when this branch branched off. And in that case, you can analyze those values for the STRs, decide what SAPP is thinking of as the modal haplotype on a first run for this group, compare them, and look at any of those differences between those haplotypes and figure out which the modals were likely, which the ancestrals rather were likely to be. And then if the modal is different from those, if the calculated modal is different from those, you can decide what to adjust. Somewhat more art than science, but if you again have the old values to look at, you have the actual calculated modals to look at for your group, and you have a sense for how fast each of these STRs can mutate, you can get a pretty good idea of what the ancestral haplotype was likely to be, and you can come up with any adjustments from there. Now, I talked a couple of times in this explanation of modal about what happens if you know the haplotype for an earlier group, the ancestral modal of a much larger group that your group descended from, and you know where the starting position of your group was, but not necessarily the group MRCA's haplotype, if you will. And that is something that you specify by use of the /haplomodal input. So very similar to modal, you put /haplomodal in this case, and then you have the string of STR values that form that modal. I'll talk about what that means in a minute. You can optionally put a label on here. I've put L226 here just for reference. If SAPP sees something in the first position that's not an STR marker value, it will assume that's the label. So it's optional, but you can put it in, and I'll show you why that will translate to the picture in just a second, or how that translates to the picture in just a second. But if you think about this, you're trying to get through the /modal input the haplotype for the group MRCA. In some cases, you'll know an earlier, larger group's haplotype that may or may not be, in fact, it probably isn't the haplotype of the group MRCA itself. It's an older one. It's something that your group descended from, but there may be thousands of years between that overall haplogroup and the subgroup that you are analyzing in this input to the SAPP file. So in this case, if you call it haplomodal, what you're saying is I have an earlier haplotype that my group has descended from, and I want to see what the STR mutation history is from that older haplogroup. So in this case, haplomodal, I put in L226, I put in a whole string of STR values, and here SAPP has put above the group MRCA from the overall haplogroup L226 in this case. Here are the mutations that have occurred to get to the group MRCA. So that is essentially the difference between the haplomodal and the group MRCA's modal haplotype, either the one that you input through the /modal input or the one that it has calculated for itself. In this case, of course, it's the one that is calculated, since I have not used the same modal input because this looks a lot like the example that I used on the previous slide, and it would not have shown these mutations if the /modal had been input as the same. So why are these two important, the haplomodal and the modal? Well, that gets into this chart. So in this case, you've got an overall haplogroup. This could be L21, U106, something much older than the group that you're analyzing. And you have the group MRCA here with all of your subgroups. It's important to know which one is the modal, the likely starting point for your group, and which one is the haplogroup of the overall group here, especially if there's been a lot of time that has passed between the common MRCA of the larger group, of the major haplogroup, and the group MRCA of your subgroup here, if there's been several thousands of years, because you've had a long path for these STRs to have mutated along the path from the major haplogroup as your group split off. What happens if you specify the larger haplogroup's haplotype for the /modal is that SAPP will try to cram all of these STR mutations, the ones that it recognizes, because some may be hidden when you put it into a shorter time frame, into the branching that has occurred from the group MRCA on down. So I'll say that again. The haplomodal has a modal haplotype for a much older, probably, major haplogroup. If you specify that major haplogroup's haplotype as your /modal, it will try to fit that many, perhaps thousands of years of STR mutations into the time frame that your group is connected. That will likely lead to invalid branching. It will likely lead to much older TMRCA estimates, and it may even lead to more examples of parallel mutations or more assumptions of parallel mutations than have actually happened. And so that's why a lot of people, when they put in the /modal, they say, well, I'll just take the modal of my larger haplogroup. That's a very dangerous thing to do, because it will likely skew SAPP's analysis off in a different direction. So the haplomodal is there in case you want to show the branching from the larger group to yours. That has no effect on the branching decisions that are made below the group MRCA. The /modal is used then if you want to affect the starting point for your own group analysis and where SAPP assumes the group MRCA started as a haplotype before all the branching occurred that led to your group. Okay, now let's cover a slightly less complicated option. We'll talk about the STR Set option. This is one where you've got a branching tree, you've already produced your output tree from SAPP, and when you analyze it, it looks like the STR mutations are not quite right, and you want to adjust with very fine control how SAPP has made its decisions. So for instance, on the left-hand side here, we have a node 94 that has two kits underneath it. And SAPP has taken the two kits and decided that STR number 458 has mutated from 17 to 18 here, going down to kit 109463. Suppose you look at this and for some reason, I don't know why, but for some reason you decide that no, actually 456 went to 18 earlier, and 134599 actually had a back mutation back to 17. So the SAPP mutation history tree is not quite right. What you can do is say /STR Set, change node 94 for marker 458 to 18. Doesn't matter what it was before, it'll set it to 18. And what that does is, if you look over on the right-hand side, we already know that 458 was 17 before this. So what it says is, okay, now at node 94, 458 has gone from 17 to 18 here. Now, if we look back down at the old kit 190463, that means that 458 didn't change along this branch, of course, because it was already 18. But over here for F134599, it says that we also have a back mutation for 458 from 18 back to 17. This is something that you can do when you know that the tree is wrong for whatever reason, but it's something to use very sparingly. You can change the settings in SAPP and really, frankly, mess up the STR mutation history tree if this isn't done correctly, especially if SAPP redraws the tree and changes the numbering of the nodes. Like I said before, you will definitely get into trouble if you use this and you don't update those node designations, because then it will be changing the STR on a completely different node, which is not what you want, presumably. You can put multiple STRs along this on the same line, the way that the format is specified down here at the bottom. So essentially what you're doing is you're changing the haplotype, the STR haplotype, at any given node to a particular set of values. Now, STR Set only works on nodes. You can't do it with kits. And the reason that you can't do it with kits is if you want to change the STR value for an STR in a particular kit, you can just go back to the input file and do that in the STR data section. So those subjects were actually the simpler ones to talk about when it comes to tweaking the tree, changing how SAPP produces the output phylogenetic tree. There's also a few more options that are more in the advanced section. These are things that to change when you really understand the basis of STRs and the how SAPP operates on the tree, how it does its various prioritizations, etc. And we'll talk about those options if you want to get this far and make really fine adjustments to the basis of SAPP's decision making. So the first pair are called /STR Order and STR Weights. And these are the only pair of sections in SAPP that are complementary. You must have both of them in order to have them take effect. Their names are pretty self-explanatory. STR Order changes the order that SAPP knows the STRs are in. So internally, by default, it has the 111 markers that are normally produced by family tree DNA. You don't have to put all of them in, but if you put any, you have to put the first set of them. So you can do up to 37, up to 67, up to 111, up to how many you want, but they have to be in the same order. As many as you give it has to be in the expected order. So in that case, the original one is, as you know, 393 followed by 390, followed by 19, 391, etc., all in the standard family tree DNA order. If your data is in a completely different in a completely different order, or if you have a completely different set of STRs to analyze, you can put those labels in through the STR Order section, and you just list all of those labels in sequence. And if you did that for as many STRs as you have here, it would produce those labels instead of the original ones. Now, what happens is, of course, if you do that, you have to then have your /STR data section be in that new order. So you would really only do this if you have a group of data that is not in family tree DNA order for some reason, and you don't want to reorder it, or if you have a completely different set of STRs that you want to analyze. This is how, by the way, you put in the full 500 set of STRs that family tree DNA produces from big Y tests. You would simply put the first 111 and add to it with the rest of the 561 total STRs, and I have already some what I call snippets, which are the sections of input file that you can simply copy and paste into your own input file if you had wanted to do that. But the way you do that is with the /STR Order section. Now, if you use this section, then the first thing is you have to refer to these labels in anything like a /ignore or a /STR Set option. So all of your sections still have to be consistent. And the second point, as I said before, is now that you've given it a new set of STRs to consider, you also have to give it the STR weights that are associated with those. And the STR weights are really just the mutation rates for those STRs. Again, just to reinforce this, these are complementary sections. You must have both of them for it to take effect. Internally, SAPP already knows the mutation rates for the first 111 STRs. You can even vary those, by the way. If you do, I have another code snippet that has the STR order for the 111, so you're basically just replacing the ones that that SAPP already has internally. And then you have a /STR weight section that has any of the existing studies that have compiled the rates for the 111 STRs. So this is an easy way to change the internal rates that SAPP has with ones that you prefer to use for whatever reason. There's about 5 of them that are listed here. There's a few more that are available for anyone who wants to use them. Again, if you contact me, Dave Vance, my email is in the About Me section of the SAPP tool. I can always send you this file so that you can play with the mutation rates if you want to. Now, I'll cover this very last option briefly. It's something that will probably make more sense if you've ever built a mutation history tree for STRs by hand. And if you do that, you know that there are faster mutating markers that are problematic for deciding on branching because they're so fast that if your tree is at all, let's say it's over about 2,000 years old, maybe 1,500, they mutate so frequently that they could be either parallel mutations or they could be single mutations that have occurred before a particular branch had occurred. And it's often hard to tell which, but SAPP makes decisions based on recognizing what we call signatures in the STRs, which are combinations of STR mutations that stand out of the data as belonging to a subgroup that defines kits that are more closely related to each other than they are to everybody else. And SAPP makes good use of signatures in order to parse out the data and build the tree. But like I said, the faster mutating markers like CDY A and B, 712, 710, 576, 650 are among the faster mutating of the markers in the 111 set. Can be problematic, and you don't necessarily want to recognize them as individual signatures. But everyone's tree varies. Everyone has had slightly different kinds of statistical mutations. The STRs have conformed either closely or not very closely sometimes to the statistical norms in any subtree, especially if you have very few kits. There isn't enough data to really mirror a statistical normal bell curve for how the STRs have probably mutated. So the default in SAPP, if you look at this graph is the genetic distance and the mutation rates. Now, mutation rates for pairs of STRs or 3 STRs or 4 are simply the weights of those mutation rates then get multiplied because the events are separate, and the odds of those events happening are the multiplication of the two. And so if you have 2 or 3 or 4 signatures, if you have 2 or 3 or 4 STR signatures, you get odds down here in the lower left. The normal, I'll say threshold for how SAPP recognizes signatures is set about here. So it will normally recognize most of the single slower mutating markers as a signature, and certainly any double or triple or higher number of STRs involved in a signature will get recognized. But the genetic distance will certainly matter as well. So if the genetic distance is very low, if those kits are related to each other within a closer time period, it will recognize the faster mutations as a signature, but not up to 650, 576, 710, or 712, or CDY A and B on their own. That's as the genetic distance goes up, it needs to recognize a bigger and bigger signature, or a rarer signature, perhaps is the better way to say it, to be a signature, because the genetic distance is so large that these are probably not related within a closer time period. Now, in fact, this actually changes as SAPP's analysis goes up the tree and gets into the older branches, but we won't go into that right now. In your data, you may decide that it needs to recognize the faster markers as single mutations. If that happens, what you want to do is expand this threshold out to something closer to the blue line, which is, if you did that, it would recognize every single marker as a possible signature. That doesn't mean it's going to force a branching on that marker. It simply means it's going to use that marker as a single possible signature in its branching decisions. So what happens is you have a /options section. You simply put the word p factor with a number after it. The default for this red line down here is p factor 80. If you drop that factor down to 4, it will actually relax this line all the way up to the blue line, and that will recognize any single STR as a possible signature. If you raise it, you can raise it up to infinity, but if you raised it all the way up to 17,000, that would that would draw this line so restrictive down here that no single STR would get recognized as a signature. It would still recognize doubles or triples or quadruples or any signature that's made up of more than 2 STRs or 2 or more STRs, but not one single one. So that's something which, again, you have to know what you want to expand or contract. It may be that you want to recognize a particular STR, and you have to know if that STR is faster mutating or slower so that you know what to set this for. But what happens is it changes how SAPP recognizes the single STRs primarily, and it will recognize those at closer GDs a lot faster than it will at the ones farther out. Now that's really the last, I'll say, detailed or mathematically based option that I'm going to talk about in this presentation. The other things that I'll close with are just a few of the other /option parameters that you might want to use if you want to change how the tree is output. So just a general comment about using the /options section. I've talked about it in a number of cases already in this presentation, but I want to reinforce that it's really just one section. You put /options, and then you put as many of these options. You can put any of the ones that we've already talked about, or you can put these that I'll talk about in a minute. Obviously, some will negate others. If you put an option in there about drawing the tree, but then you say text out to change the tree to a textual output, it may not draw it the way that you specified in a different option because it's now producing text instead of a tree. So your options have to make sense together, but they can all be in the same section because you're specifying different parameters. In this case, we'll talk about 2 new options. One is no TMRCAs, and that simply suppresses the reporting of TMRCAs on the tree. So the green section, or the green text that gives the TMRCAs, if you don't want that on the tree, you simply say no TMRCAs, and it suppresses that. The other one is one that you may not want to use because one of the points of SAPP is to produce the STR mutation history. But if you're doing this for presentation purposes or you want to simplify the tree for some reason, you may want to suppress the mutation history of STRs that it normally reports. That's the black text that shows above the kits and the nodes under normal circumstances. Again, you simply say no STRs, and that should be a capital S in the upper box there. But if you said no STRs, it will suppress the reporting of the STR mutation history. So those 2 options are ones that you can use if you want to change the output. Another option is called the show reasons parameter. Now this one, if you've seen some of the earlier videos, you know that the way SAPP reports the certainty of a placement of a node or a kit is by the thickness of the line. So these lines, for instance, are the thicker blue lines, which indicates a higher confidence in the placement of those kits and nodes. The other 2, so this is high confidence. SAPP represents a medium confidence through a thinner blue line and a low confidence with the thinnest gray line. So that's the normal way that you look at the tree and decide whether a placement is confident or not, is through the thickness of the lines connecting the boxes. You can add more information to that if you want by putting options and the phrase show reasons in the options section. And what that does is it will add this text underneath every node and kit, which is a bit more detail about why it put that node or kit where it did. Now, this only is in effect for this kit or node, and it talks about why it put it here on the tree. So it assigns it first a grade, A minus, A minus, B plus, B minus, C plus, C. I think it goes down to D. And so it will give it a grade, a bit more finer assessment of its confidence there. And then it says why it put it here. In this case, it was following a signature that was 385B equals 13, which was taken from above this somewhere, but this kit had that signature, and also this STR and that STR, so it was actually a 4 STR signature, which is pretty confident, and it also had some supporting SNPs and genealogies to go by in order to put it there. So all of these have a grade. Well, these two have a grade of B+. This one here has a grade of A-, probably because the signature here is 6 STRs instead of 4, and this one here has the same signature, also has supporting SNPs and genealogies. So you get a little bit more information there about why it's making the decisions that it's doing, if that's useful to you in your analysis. Then you have an option to simply move some text around on the screen. And the example I've put here is one where I was doing some analysis on the 500 STRs that SAPP has, that SAPP can use from the Big Y analysis that is produced by Family Tree DNA. So in this case, of course, it's analyzing 500 STRs. It's putting that mutation history on the output tree, and if you had the mutation history showing up above the boxes, it would overlap on each of the boxes and the nodes and essentially make the text that's in those boxes completely unreadable, which is probably not what you want. There's various ways to handle this. You could suppress the reporting of the STRs entirely with the no STRs option that we talked about before, but one option is you simply say off right in the options section, and what that does is it shifts the entire mutation history report to the right, away from the spot immediately above the kit or the node. And that makes it a little more complicated to read, because you have to know that, for instance, this text belongs with this box, not the one to its right, because that is this text. You have to shift each of the texts over to the left in your mind to be able to know which boxes they will go with. But it does give you a way to analyze the data if you need to, if the mutation history is going to overlap on the rest of your boxes. The next option to talk about is called Show Modals, and this is an option where you can add information to the table that SAPP already produces, where it just repeats all of the STRs that you input in the STR data section. So at the top of this example, you've got the last few kits that are in that normal box. This would be bigger normally if I had included the full table, and it would have all of the kits and all the STR data that I had put into the /STR data section, along with the calculated group modal for that section. And now that I've added show modals, what it does is it lists beneath that for any node that has a label that's a SNP or a genealogy label. So those are the more important of the nodes in your tree. It lists what the haplotype was at that given node. So now you have the SNPs in this case, and sometimes you have a range of SNPs, if you remember that convention of using the brackets to denote where a SNP could have occurred in several places on the tree. And it will show you this haplotype that it has calculated at that point in the tree. It's a way of extracting a little more information out of the SAPP analysis. It gives you essentially the modal haplotype, which is assumed to be the ancestral haplotype at each of those locations. So it's another convenient reporting tool for you if you want to decide what the haplotype is for a given SNP or a particular ancestor in your tree. And the last one is called Show Mutations. Again, this is a rather specific option for those who like to analyze their tree in a little more detail. It gives you some numbers that you can plug into various formula to do some additional analysis of your own. The information that it gives, first of all, is the total tree span in generations. So this is the span, meaning the sum of all the branches. If you add up the ages of all the branches on the tree, you get to a number of generations that doesn't equate to elapsed time. It equates to the number of generations total for all the branches of the tree. So in this case, that's 1,447 generations. It'll also translate that into years. It then gives you the tree age, which is simply the elapsed time since the group MRCA, which is really the same as the TMRCA that's reported on the group MRCA box on the tree itself. That the comparison between the span and the age of the tree gives you how bushy it is, essentially, how many branches have occurred overall. Obviously, the span is also tied to the number of kits that you've put in. That will also affect how bushy the tree is by how many descendants there are that you're analyzing. But that's data that sometimes can be useful for determining, for instance, the odds of there being back mutations that don't exist on the tree, that aren't shown on the tree, rather, that a particular STR might have mutated forward and then backwards and you don't know it. You can estimate the percentage of that or the odds of that happening and so on from that kind of data. The other thing that it gives is a table of each STR that it has used, 111, 500, however many you put in. It gives you the predicted rate so that you have the internal rate that SAPP used in its calculations. It gives you the actual rate, which is the number of mutations that have occurred on the tree and the calculated mutation rate over the time span that the tree has existed based on that number of mutations. So this is basically just a mathematical formula that calculates what the number of mutations per generation would have to be to have produced this many mutations in this time span. And then, of course, it gives you the actual number of mutations that it is calculated, which gives you a nice way not to have to go count them on the tree itself from the mutation history. You can simply see how many mutations this has come up with. Whether or not this data is useful to you depends on how much analysis you want to do of the mutation rates and the number of mutations on the tree. It does give you an easy way to look at a few of the faster mutating ones, or the faster, I'll say the largest number of mutations, and confirm that those are from the faster mutating markers, which is what you'd normally expect. And that brings us to the end of the advanced topics. I think I've probably covered enough for one video. I hope this was useful. And again, go back to some of the other videos. If this didn't make sense or that didn't answer some of your questions, see if it's covered in one of the other videos. If not, you can always send me a quick note and I'll get back to you as quickly as possible. Thank you for listening.